Okay, so beam subjected to bending moment M. Okay, what we're given is the dimensions of the beam, and we need to compute M that causes the bar to yield, and we're given sigma, this is sigma y, is 36 KSI. Is kilo pound per square inch. Okay, so what happens here, what's going on here is M is a moment you apply, and you can start off with 0 moment and you keep increasing M. At some point of time, when the stress in the beam becomes sigma y, it will start yielding. So you need to compute that maximum possible moment M if that happens. So here, there's a relation between M and sigma, and I just write it from the previous page. M divided by I is sigma divided by y. I don't need the part involving E and R. So here, M is the unknown. Sigma is going to be sigma y, it's known. Here, hopefully, we can compute what I is and what y is. Okay, so we want to compute so let's write this as M equals sigma y times I divided by y. Okay, now something to note is when you have this cross section, and clearly the neutral axis is right in the middle, we know that the way the stress would vary is the stress is 0 here. It's going to be compressive on top, right? Because look how M is. It's going to sag or be convex or make a shape like this. So on the top, it's going to be compressive. So I'm going to draw compressive stress. And then tensile stress. So this is sigma y, sigma y. So this is negative y plus sigma y. Okay, so maximum stress occurs, max stress at y equals h divided by 2. Okay, it could also be based on the min stress. We're assuming that the yielding can both sides have the same stress. It's not really clearly told here, but let's assume that's the same. It doesn't really matter if you go with the max or the min. The magnitude is the most important. But here, note that it's always at h divided by 2. So you don't have any option. You can't put y equals 0 because at y equals 0, which is this, your stress is 0. So there will be no stress. So we know what y is. Let's call this, if you want, b. Let's call this h. So we know that this is h divided by 2. And now I need to compute I. Okay, I is the moment of inertia. And you don't really need to memorize this. There is a table in the book, and I'll give that table to you. We just have to read off the moment of inertia from that table. Okay, so if you have the book, you need to see table A18. Okay, so let's look at table A18. Just copied it from the book. Okay, so it gives you area Ix, Iy, Ixy for rectangle, for a circle, hollow circle, and there's another page. And this gives for some more complex geometries like a right triangle and different configurations, and then quarter circle. I'm surprised they didn't give a semicircle. Yes, that's table A18. I'll give it to you in the notes. You don't have to buy the book just because of that. Okay, so I completely forgot. So we need to compute the moment of inertia of rectangle, right? So for this, we want inertia about x-axis. So we remember we call this h, we call this b. So we want ix. Ix is ph cube divided by 12. B being the axis along x, and h being the perpendicular to the x-axis. So with that, let's go back to the problem. And we can write I equals ph cube divided by 12. I've already have I've put the names h and b here. So we all set to now solve this. So we have m is equal to sigma y 1/12 bh cube. Y is h divided by 2. So we have sigma y b h square divided by 6, I think. So sigma y is 36. B is 0.8. H is 2.5 square divided by 6. From this, we get m equals 30 kip inch. Okay, that was sort of the starter. Let's do sort of warmed up. Let's do a slightly more involved problem. So what's given is the ultimate strength, 60 ASI, the factor of safety is 3. So the first part, we need to compute m. The second part, we need to compute the radius of curvature. Well, the radius of curvature actually is 1 divided by r. We are given E is 10.6 times 10 raised to 6 ESI. Sure, yeah. Paper towels. You want to wipe the board? Yeah. Whiteboard? Yeah, the whiteboard. You can use this and maybe. No. No? No. It just leaves everything on the eraser. Oh. All the writing makes on the board. Yeah, I'm sorry. He must be surprised to see two students in the class. His class is full. Okay, so how do we go about doing this? Let's try to work in reverse. For A, what we need is m. And so the only formula we know at this point is m is related to sigma. M is sigma divided by y. And if you're given the geometry, we can pretty much compute I, Y, M is the unknown. And here, unfortunately, sigma is also unknown. But perhaps we can compute the allowable stress. Sigma is, in this case, the allowable stress. Maybe we can compute the allowable stress given that we know the factor of safety. So the factor of safety, N, is max stress divided by allowable stress. So the max stress is like the most you can get from any material is the ultimate strength, right? It's where the strength achieves its peak. So if you look, this is like a review. So if you look at the curve of stress versus engineering strain, you see that it goes something like this, where this is SUT, and then it goes down. The yield strength is somewhere here. Okay, but that's the ultimate strength. So here, SUT divided by sigma. So N is 3. SUT is 60 KSI. Sigma is unknown. From this expression, we can compute sigma. It's 20, same units as SUT, KSI. Yeah, so now it seems like we have Y. We only need to compute I and Y. Okay, Y is actually kind of trivial because it's a regular geometry, even though it is a rectangular hollow section. We know that the center is going to be at C around those axes. So we are not really worried about too much about Y. It's going to be half of the height. But the other one is something which we need to figure out, I. It's not clear what I is because if you go back at the table, we don't have a formula for Y for a hollow rectangular section. So we need to do that computation ourselves. Okay, so what we know is, so Y is clearly this is Y. It's going to be 2.5. So Y is there we have Y. We need to compute I. Yeah, let's compute I. Okay, so what we know about I from looking at this table is that I for a rectangular section, a solid section, is BH cubed divided by 12. Let me translate that over here. Okay, so the formula for I is BH cubed divided by 12. This is from table A18. Okay, now we're going to attempt to use this formula to compute the inertia, moment of inertia of hollow sections. What we do here is we can decompose this a hollow section. So let me draw that first. As one solid section minus the inner section. So the inertia of this is going to be the inertia of the solid section minus the inertia of the inner solid section. So all that needs to be done is we need to fill in the dimensions. So the dimensions of the outer one is 5-inch (3.25). I'm just writing it from the previous page. And then the thickness here is actually 0.25. It's 0.25. So in order to compute this height, we need to do 5 minus 2 times t, right? This is t and this is t. So if you do 5 minus 2 times t, we get 4.5. And then same for this one. B is going to be 3.25 minus 2 times t. So it's going to be 3.25 minus 2 times t equals 2.75. So I, the left side is unknown. I1, we know that. It's basically using this formula. BH is 3.25. Height is 5. So 5 cubed divided by 12 minus the width, which is 2.75 for I2 times height, 4.5 cubed divided by 12. Crunch the numbers, comes out to be 12.97 inch raised to 4. Now we're all set to compute m. Its m is sigma I divided by y. Sigma, we had computed 20 ksi from the factor of safety. I is the answer is right above here. And then y is, remember, it was height divided by 2. I think I put it down somewhere here. It's 2.5 inches. So that comes out to be 103.8. Inch. So that's part one. Part two, we need to compute 1 divided by r. So going back, we need to compute here 1 divided by r. So we can do that now. So again, we go back to the formulas. M divided by I is E divided by R, sigma divided by y. You can use either these two or these two. It's up to you. Since we know everything on the left side, we also know everything on the right side. It's usually better to use something which we have more confidence, sigma by y, perhaps, because you did that calculations, you could be wrong. So better off using sigma divided by y. So let's use that. We need to compute 1 divided by r, which is radius of curvature. It's simply sigma divided by y times c. Sigma is 20 ksi, y is 2.5 inch. E is given to be 10.6, 10.5, 10.6 times 10 raised to 6. So 1 divided by r comes out to be 7.55, 1 e negative 4 inch raised to negative 1. Do you know what a radius of curvature is physically? Bends, right? Yeah. So this is r. This is a arc. This is r, and this arc is a measure of 1 divided by r. So if r equal to infinity, that would be a flat ground. That's r equals infinity. So if r is very small, well, if you can see here that r 1 divided by r is very small, 1 e negative 4. So r is actually a really rather big number, which means that when this beam bends, it doesn't really bend. It doesn't really, it's almost flat, so to say. And that's what we expect, right? When you bend something, if it's going to show a big enough r or small enough r, that means it bends a lot, which means it's not safe. Here, r is small, r is, sorry, 1 divided by r is small, which means that r is big, which is almost flat. Like this example here, r equals infinity. Okay, so if r is infinity, 1 divided by r is close to 0, right? That's what it is, close to 0. Well, not quite, but close. Okay, with that, let's move on to another problem. This problem showed you how to combine inertias to come to the net inertia. Here's a problem which goes a step further. It introduces a T section, and now it's not only a problem of computing the inertia, but you also need to figure out where the neutral axis is, because you cannot guess the neutral axis just by looking at the figure. It's not midway, right? Okay, so the beam shown is acted upon by moment m, which is shown. Determine the maximum tensile and compressive stresses on the beam. Okay, if the object is symmetric, like we've seen before, the compressive stress and the tensile stress is the same, equal and opposite, right? But this one, you will see that, in fact, it's not true. The compressive stresses are different from the tensile stress because it's not a uniformly, it's not axisymmetric. So let's see what's given. It's m pre kilonewton meter. Okay, we are asked to find the maximum tensile stress, maximum compressive stress. Okay, we know that m divided by I is sigma divided by y. And so in this equation, we know m, we have to compute I, but we can actually compute it because we know the dimensions. So y is something we need to figure out the neutral axis. So we'll have, in fact, we'll have two answers, one for, let's call this, one is yc, one for yt, which will give us corresponding sigma c, sigma t. So we need to find where the neutral axis is first. And then once we know neutral axis, we can compute what yc is. So for example, if the neutral axis is here, let me call that NA, then you can see how this is applied. It's this way. If you see from here, It's counterclockwise. If it's counterclockwise, then anything above would be what? Compressive or tensile? Tensile. Because the top first surface will be stretched. The bottom surface will be compressed. So this would be YC, this would be YT. And that's how they'll appear here. And then you'll get sigma C, sigma T. Okay, that's what we're going to do. I'm going to erase this. Okay, let's get to computing the most important things here. The things which are clear the unknowns are I and Y. Let's compute that. Let's compute Y first. So one, we need to compute the neutral axis. Okay, so the way we compute neutral axis is the formula integral y dA divided by integral dA. So I'm just going to redraw this T section. Okay, fix an origin of your choice. Doesn't matter where you want it. We can see that it's actually going to be symmetric about this axis, right? So why not choose the origin right here? So this will be my y. Let's put in the dimensions. I'm going to skip the units, save some space. 20, 40, and 30. Okay, so because I chose 0, 0, and y to be downwards, x is clearly at 0, right? So x is not a problem. You just have to compute the y, because that's what will actually come in the equations, the neutral axis. Okay, so what I'll do is here, I'll break it into two geometries. That's my first geometry. And the second geometry is here. Let's call them 1 and 2. And now my y bar is y1 a1 plus y2 a2 divided by a1 plus a2. Okay, when I compute y1, it's basically the center of the centroid of the first geometry. Okay, from the axis shown 0, 0. So clear that the first center is right here in the middle. So that'll have a distance of 10 mm, right? Half of 20. Next is the area of the yellow part. So that's going to be the length times width. So it'll be 90 times 20. That completes A1. For Y2, it's going to be the center of the pink, or the second rectangle. So you can see that the distance this is 40, so this is going to be 20, but I need to find the distance from the origin. So from the origin, the distance is 20 plus 20. 40 is Y2. And then the area of the green, or sorry, the pink section, pink rectangle is 30 for the base, so the width, and 40 for the height, divided by the area of 1, so it's 90 times 20, plus area of 2 is 30 times 40. Apparently, this comes out to be 22 meters or millimeters. So where is 22? Okay, this is 20, so 22 must be here. This is x is 0, y is 22. That's where the centroid is. Slightly below the yellow rectangle. Yeah, so that's also the place where the neutral axis is located. Okay, let's do the second part. Now we've computed neutral axis. Let's compute the moment of inertia. Okay, the moment of inertia is always computed about the centroid. So we need to compute about that point, 0, 22. Yeah, that's for the reference. Let's call this point as G. I need to compute I for G. So second is compute I. Okay, so for that, we'll follow a similar procedure. We'll break it into two rectangles. The first rectangle is shown. It has the dimensions of 20 and 90. But the centroid is right here at 2 millimeters below that, right? So it's 22 millimeters from the top, so 2 millimeters from the end. And the actual centroid is right here, middle. So let's call this, let's call that G1. And this point is G. G1 is the centroid of the yellow rectangle, number 1. Okay, now what I'll do is to compute let's call that G1 bar, okay? Okay, so that's the centroid of the complete system, but I want to compute for 1. So I just have a notation, say G1 bar. So that would be I of G1 plus, there's something called parallel axis theorem, which tells you what's the inertia about an axis not passing through the center. So the axis which we want to compute the inertia is G1 prime. That does not pass through the centroid of the yellow rectangle. And so what you need to do is you need to compute the distance between G1 and G. So I'll put R, G1, and G1 prime square times the area of 1. Okay, so this is parallel axis theorem. This part, just this part is the parallel axis theorem. Okay, so IG1 is, well, we know the inertia of a rectangular plate. That's in table A18. I'll not go back again, but it's going to be 1/12 times the breadth or width, 90, times height cubed, so 20 cubed, plus the distance between G1 and G. So remember that this is 10. G to the edge is, bottom edge is 10, and G, the bottom edge to G1 is 2 mm. So this height, well, let me put it here. This is 10 mm. So it's 12 square times the area, 90 times 20. Okay. You can do the same thing for the pink rectangle. For that one, G is right here. Let me call that G2 bar. The actual center is here, G2. The dimensions are the height is 40 and the thickness is 30. And the distance between G1 and G2 is, well, it's 20 minus 2, so it's 18. So I G2 bar is I G2 plus R G2 G2 bar square times A2. So again, use the formula from table A18, 1/12, 30 is the breadth, 40 is the height, G1, G2, G2 prime is 18 square, area is 40 times 30. Okay, so the net inertia I about G is IG1 bar plus IG2 bar. So if you do the math and add it up together, you get actually get a 860 8.68 times 10 raised to 7. Actually, this is in meters. M raised to 4. It's a very small value, 1e negative 7. So this is what we were after. Okay. So let's remind ourselves what we're trying to do here. If you go back, we are trying to compute the stress sigma C and sigma T. And for that, we need YC and YT. YC and YT being the distances from G, what we computed, to the edges. Okay. So if you have this particular, I'm going to redraw this figure so we'll see what sort of re-explain this. We have this T section. Okay. And if you look at this, the moment is this way, counterclockwise. The moment is this way. We know the neutral axis, it's just beneath the T. Okay, so as we pointed earlier, the top section is going to be under tensile stress. We have sigma T. The bottom section will have sigma C. We want to know what this height is. Let's call that YT. And the reason why we want that height is because the maximum tensile stress occurs on the edges, on the surface. Doesn't occur close to the neutral axis, as far as possible from the neutral axis. So YT here is, see, so I think it's 20 plus 2, 22. Because of that neutral axis slightly below, and YC is, I think it's 40 minus, so it's 40 minus 2, 38. And then we know what IG is. I equals IG. We computed that as 8.68 times 10 raised to negative 7. Okay, so one, if you want to compute sigma C, so the formula is sigma M divided by Y is sigma divided by I. So we can write sigma C is MYC divided by I. So M is given to us, it's 3 kilonewton meter. So that's M. YC is 38 mm. Let's convert it to meters. So negative 3 divided by I, 8.6. This is M raised to 4. 68. So doing the math, sigma C comes out to be 76 megapascal. In the second part, we need to compute sigma T. That's MYT divided by I. M is the same as before, 3000 Newton meter. YT is going to be 22 mm. So convert that to meters, 10 raised to negative 3. I is what we computed earlier, 8.68, 10 raised to negative 7. And if you do the math here, you get sigma T is, oh my God, I did a mistake. So this is not correct. This is, I switched them. So this is 131.3 megapascals, and this is 76 megapascals. Okay. Not unsurprisingly, sigma C is greater than sigma T, because you can see that this distance is greater than YT. Okay, so it will fail first in compression if it's the same yield strength or ultimate strength, which explains tensile as well as compressive failure. Then this particular section will fail first in compression because the stress is much higher than in tension. If you change the bending moment to the other way, clearly it will be the other case, right? This is for M to be the way it is shown. If you change it to be clockwise, then sigma C and sigma T will just reverse.